talking about these three laws: Boyle's law, Charles' law, and Guy-Lussac's law. In each of these laws, something is constant. One of our variables is constant. So in Boyle's law, temperature is constant. In Charles' law, pressure is constant. In Guy-Lussac's law, volume is constant. So I wanted to talk about what if those are not constant. And so what if temperature is not constant? What if pressure is not constant? What if volume is not constant? So one thing you might notice when I put all of these together is pressure is always on the top of the equation. Volume is always on the top of the equation. Temperature is always on the bottom of the equation. So we can actually combine each of these equations to get the combined gas law. So this would be the law that we use if none of those variables are constant. So if temperature is not constant, if volume is not constant, if pressure is not constant, but all of our variables are changing, we would use the combined gas law. Another thing that I actually want to point out to you is that the combined gas law can actually be useful to you if you forget which law to use. So if I have the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2, and you're looking through, and you find this in your reference packet, and you're like, okay, I know that my problem has pressure, it's got volume, it's got two pressures, it's got a volume, and I'm solving for another volume, but I don't know which equation to use. I don't have a temperature. Cover up temperature, and there's your equation. We're left with Boyle's law. Okay? And so you have a similar scenario. Let's say your problem gives you an initial volume, an initial temperature, a final volume, and you're solving for a new temperature, which means that pressure is constant, or you're not given a pressure. Cover up pressure. What do we have? Charles' law. Same thing. Once again, if you're given an initial pressure, an initial temperature, we're changing the temperature. And you're solving for the final pressure. Volume is constant. Cover up volume. And we're left with Guy-Lussac's law. You might have heard me say that is in your reference packet. It is on page 3. Under formulas, it's close to the top. P1 V1 over T1 is equal to P2 V2 over T2. So here it is right here. All right. So using all of this information, we're going to go ahead and do 2 practice problems. In case I forget to say it, after we do the first one, if you feel like you're comfortable and you want to try the second one on your own and check your answer at the end, that's fine with me. Or even if you feel comfortable because we've done each one of these 3 laws, if you want to try the first problem and check your answer at the end, that's fine. All right. So these problems are a little bit longer since they have more variables. You should be given 5 variables and 1 variable that you are solving for, or 1 variable that is unknown. So in this question, helium gas at a temperature of 220 degrees Celsius and confined in a 5-liter cylinder exerts a pressure of 3.2 atmospheres. If the gas is released into a 10-liter reaction vessel, so it's going from 5 liters to 10 liters at a temperature of 30.6 degrees Celsius, what will be the pressure inside the reaction vessel? All right, so this is a lot of stuff. I'm going to go ahead and write down all of my variables. So what does it give me first? It says 20 degrees Celsius. So Celsius is a temperature. Then it says in a confined in a 5-liter cylinder. So I spelled cylinder wrong. And 5 liters is a volume. Exerts a pressure of 3.2 atmospheres. If the gas is released into a 10-liter reaction vessel, so I have another volume. You might notice as I go through, I like to keep my variables in the same order that I started with, so T, V, P, or temperature, volume, pressure. So I'm going to do that the same when I go down. So I have volume, 10 liters, and then at a temperature of 30.6. Okay. You'll notice I haven't assigned any of these as 30.6 degrees Celsius. You'll notice that I haven't assigned any of these as T1 or P1 or V1. However, I have a good idea of where they are, but I will tell you, you need to read your problem carefully. So it says a helium gas at a temperature of this, confined in a 5-liter cylinder, and all of that is exerting this pressure. So basically everything in this section of the problem is my initial scenario. That's my gas at that first time. So time 1. Then it says the gas gets released into a 10-liter reaction vessel and the temperature changes. The temperature increases to 30.6. So these are both my final sets. Just because in this problem we had our initials all in one set and our finals all in another set doesn't mean that every problem is going to be like that. Make sure you're reading your problems carefully, and because sometimes they will switch things up and give you the initials and the finals together. So pay attention to how things are worded. Okay. We are solving for P2. Before I can solve, my temperatures are given in Celsius. I need to change them to Kelvin. In order to do that, I have to add 273. So 20 plus 273 is 293. 30.6 plus 273, 303.6. All right. Now, one major way that I can tell that this is a combined gas law problem is that I have 5 variables, and they are all changing. So I can write down my combined gas law equation. P1, V1 over T1 is equal to P2, V2 over T2. All right, I am solving for P2. I'm going to get P2 by itself. In order to do that, I'm going to multiply by the inverse, which means opposite. So I'm multiplying by T2 over V2. And I have to do that to both sides. So I'm multiplying by T2 over V2. So notice we've got a lot of variables going on. So even more important than when we did Boyle's law, Charles' law, and Guy-Lussac's law when you go to plug in, make sure you're putting everything in the right place and assigning each one of these numbers to the right variables. So now I'm going to have P2 is equal to T2, so T2 is now at the top, multiplied by P1 times B1 over B2 times T1. So I've rearranged my equation so that I have P2, which is the variable that I am solving for. Now I can plug in the numbers that I have for each one of my variables. So my first variable is T2. So T2 is 303.6 Kelvin. Multiplied by, second one I have is P1. So make sure you're plugging in P1. Well, I'm solving for P2, so I can't plug that in. But I have 3.2 atmospheres. Multiplied by my V1 is 5 liters. I do have 2 volumes, so make sure you're doing volume 1 and not volume 2. When we go to the bottom, we do have volume 2, so that's our 10 liters. Multiplied by, now we have T1, so make sure you're plugging in T1, 293 Kelvin. Alright, and again, before we solve, we want to make sure everything cancels. I have a pressure here. We have a lot of units for pressure. We have kPa, millimeters of mercury, torr, atmospheres, so I need to end up with one of those units. As I look across, I have atmospheres. Atmospheres don't cancel with anything, meaning I don't have atmospheres anywhere on the bottom. I want to make sure also that all of my other units cancel. So I have Kelvin, and I have Kelvin on the bottom. So Kelvin cancels. I have liters, and liters on the bottom. So liters cancel. I don't have any other units, so I will be left with atmospheres. Now, I know, not liters, atmospheres, that I can accurately plug in these numbers. Alright, so I'm going to do 303.6 multiplied by 3.2 multiplied by 5. And when I do this, I hit equals after I've multiplied by these. And then I hit divided by, and I put parentheses around the bottom. If you want to do them as two separate, that's fine, as long as you get the correct answer. Divided by 10, multiplied by 293. I get 1.657, so I'm going to round that to 1.66. And we have successfully done our first combined gas law problem. I'm going to move on to the next one. So this question says a sample of argon gas at a pressure of 1.1 atmospheres fills a flask with a volume of 300 milliliters at a temperature of 25 degrees Celsius. If the gas is transferred to a 500 milliliter flask at a pressure of 2.5 atmospheres, what is the temperature of the new flask? Alright, so I'm going to do the same thing that I did with my last problem. I'm going to start writing down variables. When I read these problems and I start to see variable after variable after variable, I like to write them all down because it helps me figure out what kind of problem I'm doing. Alright, so a sample of argon gas at a pressure of 1.1 atmospheres. So I know I have a pressure. 1.1 atmospheres. Fills a flask with a volume of 300 milliliters. At a temperature of 25 degrees Celsius. If the gas is transferred to a 500 milliliter flask, so I'm changing the volume now. Alright, so let's read through our problem actually before I go to write these down. I think it's similar to the last problem. Everything in this part of my problem is my initial set of circumstances. If the gas is transferred to 500 milliliter flask, and then my pressure is now 2.5 atmospheres, wants to know the new temperature. So all of these are my initial set of circumstances. P1, V1, T1. And now I have a new volume, 500 milliliters. I have a new pressure, 2.5 atmospheres. And it wants to know what the new temperature of the flask will be. So I don't know my T2. Just like with the last problem, I have 5 variables. I have 2 pressures, 2 volumes. I don't have 2 temperatures. I'm given one. I'm solving for the other. So I have 6 total variables in my equation. I know that this is a combined gas law problem. So I'm going to write that down. P1, V1 over T1 equals P2, V2 over T2. In this case, I'm solving for T2. T2 is on the bottom though. Remember, just like with my 506 problem and my Charles law problems, I want T2. If I'm solving for T2, I need to first get it onto the top of my equation, because my goal is to have this. T2 equals something. So I have to first get it onto the top. I don't want 1 over T2 equals. I want T2 equals. So just like with my Gay-Lussac problem, I'm going to show you what I think is the easier way of doing this. This is what most of my students have preferred in the past. If you do not prefer this way, I would recommend going back and looking at the Charles Law video, which shows both ways. But this is the way that most of my students have preferred. Alright, which is cross multiplication. So we're going to take P1 and V1 and multiply it by T2. That will get me T2 on the top. It doesn't quite get me T2 by itself, but it gets me halfway to my goal. Gets me T2 on the top. Okay? And then I cross multiply. I got a little ahead of myself there. Then I cross multiplied T1 and P2 times T2. Now to get T2 by itself, I'm going to divide by P1 and V1. And I'll be left with this formula. And now I can plug everything in. Again, just like our last problem, make sure that you have everything in the right location. Okay, so I have P2 first. So my P2 is 2.5 atmospheres. My V2, again, V2 is 500 milliliters. Multiplied by my T1. Oh, wait a minute. we skipped a step. 25 degrees Celsius. I can't use degrees Celsius. I have to add 273 here. And we'll get 298. Alright. Divided by my P1, which is 1.1 atmosphere. Multiplied by 300 milliliters. We're going to make sure everything cancels. I'm looking for T2, which is temperature. So I want to make sure that my answer is going to be in a temperature, and just like we just looked at, not just any temperature, I need to make sure it's in Kelvin. So I need to make sure that my Kelvin is not canceling with anything. I don't have any Kelvins on the bottom. I don't have divided by Kelvin anywhere up here, so I'm good. I also want to make sure that my other units are canceling, that I'm getting rid of them. So I have atmospheres, and they cancel with atmospheres. I have milliliters, canceling with milliliters. And now I can plug into my calculator and see what I get. So just like the last problem, I'm going to do my 2.5 multiplied by 500 multiplied by 298, and then I'm going to divide that whole thing by 1.1 divided by 300. And I get 1,128.787, so I'm going to round that to 79 Kelvin. All right. And that's it for the combined gas law.